Welcome to this coding walkthrough. Today, we'll explore problem number 1238 titled Circular Permutation in Binary Representation. In this session, we'll break down the problem, discuss approaches, and analyze their complexity. Let's dive in. In this problem, we are tasked with generating a circular permutation in binary representation based on two inputs, n and start. The integer n determines how many bits we are working with, and start specifies the number where the sequence should begin. The goal is to create a sequence of all 2n integers such that each number appears exactly once. Importantly, the sequence must start with the number given as start, and every two adjacent numbers in the sequence must differ by exactly 1 bit. This 1-bit difference is characteristic of what's known as gray code. The output should be a list of integers representing this circular permutation. To make this more concrete, let's look at an example. Suppose n is 2 and start is 3. For n equals 2, the gray code sequence is 0, 1, 3, 2. Since the sequence must begin with start, which is 3, we rearrange the sequence to 3, 2, 0, 1. Notice how each pair of adjacent numbers in this sequence differs by exactly 1 bit. For example, the binary representation of 3 is 11, and the binary representation of 2 is 10. These differ by just 1 bit. Similarly, the transition from 2 to 0, 0 to 1, and 1 back to 3 also satisfies the 1-bit difference rule. Now, let's examine another example where n is 3 and start is 2. When n equals 3, the gray code sequence is 0, 1, 3, 2, 6, 7, 5, 4. Starting from start equals 2, we rearrange the sequence to 2, 3, 1, 0, 4, 5, 7, 6. Again, notice that each adjacent pair of numbers in this sequence differs by exactly 1 bit. For instance, the binary representation of 2 is 0, 10, and 3 is 0, 11, they differ by 1 bit. This property holds true throughout the entire sequence. The sequence length here is 2 cubed, which is 8, and every number from 0 to 7 is included exactly once. Looking at the constraints, n can range from 1 to 16, meaning the sequence can grow as large as 2 to the power of 16, or 65,536 numbers. The start value must always fall within the valid range of the n-bit gray code sequence, from 0 to 2 to the power of n1. For smaller inputs, like n equals 1 and start equals 0, the output would simply be a permutation of 0, 1. On the other hand, for the largest inputs, such as n equals 16 and start equals 0, the sequence will include all 65,536 integers starting at 0. If start is not 0, like in the case of n equals 4 and start equals 5, the sequence must still begin at 5 and adhere to the gray code rule, ensuring that each transition between numbers differs by 1 bit. To begin solving this problem, we considered a brute force approach. The intuition here is straightforward: generate all possible binary numbers of length n, which would give us 2n combinations. Then, we could sort these numbers in a way that consecutive elements differ by only 1 bit, which is a property of gray codes. After sorting, we would locate the given start value within the sequence and rotate the list so that it begins with this value. While this method is conceptually simple, its computational cost is significant. Generating and sorting all permutations requires O(2 to the power of n asterisk n) time, and storing these permutations takes O(2 to the power of n) space. These inefficiencies make this approach impractical for larger values of n, especially given the exponential growth of 2n. Additionally, the extra steps like sorting and rotating further increase the overhead, which limits its scalability. A more efficient solution involves directly generating the gray code sequence for n bits using a formula. The key insight here is that the gray code for an integer I can be calculated as I(i1). With this formula, we can quickly compute the sequence for all 2n numbers without needing to generate all permutations or sort them. Once the gray code sequence is generated, we identify the index of the start value and rotate the sequence to ensure it begins with this value. This approach significantly reduces the computational complexity compared to brute force. Generating the sequence and locating start both take O(2 to the power of n) time, and we still require O(2 to the power of n) space to store the sequence. However, despite being faster and more efficient than the brute force method, this approach still requires generating the entire sequence explicitly, which can be memory intensive for large n. To further optimize the solution, we can take advantage of the properties of gray code and modular arithmetic to compute the rotated sequence directly. Instead of generating the full gray code sequence and rotating it afterward, we calculate each value in the rotated sequence on the fly. Using the formula start1, where I represents the position in the sequence, we can directly compute the gray code values adjusted for the start offset. This eliminates the need for explicit rotation and the overhead of finding the index of start in a pre-computed sequence. The process involves iterating through the range 0, 2 to the power of n1, computing the gray code values for each index, and appending them to the result. This method has a time complexity of 2 to the power of n for generating the sequence and a space complexity of 2 to the power of n to store the results. By avoiding unnecessary intermediate steps, this approach provides a streamlined and efficient solution. Ultimately, we selected the optimized gray code approach because it is the most efficient and elegant solution. By leveraging the mathematical formula for gray code generation, we eliminate redundant computations and minimize memory usage. This method allows us to compute the rotated sequence directly in one pass, making it both time and space efficient. The key insights that make this approach stand out include the simplicity of deriving gray codes using the formula I1, and the ability to adjust for the start offset without explicit rotation. Modular arithmetic plays a crucial role in efficiently calculating the rotated sequence. While the brute force method is computationally prohibitive and the direct generation approach still requires large memory for storing the sequence, the optimized approach strikes the perfect balance between efficiency and simplicity. Its reliance on mathematical properties ensures that it handles large values of n effectively, making it the ideal solution for this problem. To begin, the problem requires us to generate a sequence of binary numbers of a given length n such that the sequence follows three key properties. First, each number in the sequence must be represented as a binary string of length n. Second, consecutive numbers in the sequence must differ by exactly 1 bit, meaning it adheres to the gray code property. Finally, the sequence must start with a specific binary number, denoted as start. To tackle this, we can use a brute force approach. The first step in this approach is to generate all possible binary numbers of length n. We do this by iterating through integers from 0 to 2 n1 and converting each integer into its binary string representation of length n. For example, when n equals 3, the binary numbers generated are 000, 001, 010, 011, 100, 101, 110, and 111. This gives us a comprehensive set of all potential binary strings we can use. Next, we convert the binary numbers into their gray code equivalents. This is achieved using the formula gray x equals x XOR x1. The formula works because it ensures that only 1 bit changes between consecutive numbers in the gray code sequence, a core property of gray code. For instance, if we take x equals 3, which is represented in binary as 011, applying the formula gives gray 3 equals 3 XOR 31 equals 011 XOR 001 equals 010. This process is repeated for each binary number, and the resulting gray code values are stored in a list. Once we have the complete gray code sequence, we need to ensure it starts with the specified start value. To do this, we find the index of the start value in the sequence and rotate the sequence so that start becomes the first element. For example, if the sequence is 000, 001, 011, 010, 110, 111, 101, 100, and start equals 110, rotating the sequence results in 110, 111, 101, 100, 000, 001, 011, 010. Finally, the rotated sequence is returned as the solution. There are a few key insights to take away from this approach. First, the gray code property is guaranteed by the XOR formula, which ensures that consecutive numbers differ by only 1 bit. Second, the rotation step is straightforward and allows us to meet the requirement of starting the sequence with the given start value. However, it's important to note that this brute force approach is not the most efficient. Generating all binary numbers and converting them to gray code requires 2 to the power of n, time for both computation and storage, which is manageable only for small values of n. In terms of data structures, we primarily use a Python list to store the gray code sequence, as it allows for easy indexing and rotation. Additionally, the built-in bin function is employed for efficient integer to binary conversion. Let's analyze the complexity of this algorithm. The time complexity can be broken down into three main steps. Generating all binary numbers requires 2 to the power of n operations. Converting these numbers to gray code also takes 2 to the power of n, as we apply the XOR formula to each number. Finally, finding the start value and rotating the sequence is another 2 to the power of n operation. Therefore, the overall time complexity is 2 to the power of n. For space complexity, we need 2 to the power of n space to store the gray code sequence, giving us an overall space complexity of 2 to the power of n. It's also essential to consider edge cases. For small values of n, such as n equals 1, the sequence is simple, either 0, 1, or 1, 0, depending on the start value. For large values of n, the algorithm becomes computationally expensive due to the exponential growth of the sequence. Lastly, if the start value is not a valid binary number of length n, it's crucial for the algorithm to handle this gracefully, either by throwing an error or by validating the input beforehand. Let's go through an example to solidify our understanding. Suppose we have n equals 3 and start equals 110. The first step is to generate all binary numbers of length 3, 000, 001, 010, 011, 100, 101, 110, 111. Next, we convert these binary numbers into their gray code equivalents using the formula gray x equals x XOR x1. The resulting gray code sequence is 000, 001, 011, 010, 110, 111, 101, 100. Now, we need to rotate the sequence to ensure it starts with the start value, which is 110. Finding the position of 110 in the sequence and rotating it results in 110, 111, 101, 100, 000, 001, 011, 010. This rotated list is the final gray code sequence that satisfies the problem's requirements. The output, therefore, is 110, 111, 101, 100, 000, 001, 011, 010. The provided solution generates a circular permutation in binary representation based on the gray code sequence. First, the circular permutation function generates the gray code sequence for n bits. This is accomplished by iterating through all numbers from 0 to 2 to the power of n1 and applying the gray code formula I1 to each number. This ensures that consecutive numbers in the sequence differ by exactly 1 bit. Next, the function identifies the index of the starting number start within the generated gray code sequence. This is done using the index method, which searches for the first occurrence of start in the sequence. Finally, the gray code sequence is rearranged to begin with the start number. This is achieved by slicing the sequence into two parts, one starting from the start index to the end, and the other from the beginning to the start index. These two parts are then concatenated to form the final circular permutation. The algorithm is efficient with a time complexity of 2 to the power of n, as it generates all gray code numbers and performs a linear search for the start index. The solution handles all edge cases, including scenarios where the sequence wraps around due to the circular arrangement. This is the Java implementation of LeetCode problem number 1238, circular permutation in binary representation. It mirrors the logic of the Python solution, generating the gray code sequence, finding the desired starting index, and rearranging the sequence. Key differences include using Java's list for dynamic arrays, explicit type declarations, and the use of ArrayList methods for sublist operations. This implementation is complete and adheres to Java coding conventions. To solve this problem, we start by generating the gray code sequence for n equals 2. The total number of values in the sequence is determined by 2*n, which gives us 4. Recall that the formula for gray code is I1, where I is the index. Let's calculate the values step by step. For I equals 0, we have 0*01, which equals 0. For I equals 1, the calculation is 1*11, which gives 1. For I equals 2, the formula results in 2*21 equals 3, and for I equals 3, we compute 3*31 equals 2. This gives us the gray code sequence, 0, 1, 3, 2. Now, the start value is specified as 1. To rearrange the sequence so it begins with this value, we first find its index, which is 1. Finally, we rearrange the sequence starting from this index, appending the earlier elements to the end. The result is 1, 3, 2, 0. The final output for the first example is 1, 3, 2, 0. Now, let's look at the second example where n equals 3 and start equals 4. Again, we begin by generating the gray code sequence. The total number of values is 2 3 equals 8. Using the formula I1, we compute each value. For I equals 0, we calculate 0 equals 0. For I equals 1, we get 1 equals 1. For I equals 2, we compute 2 equals 3, and for I equals 3, the result is 3 equals 2. Continuing, for I equals 4, we calculate 4 equals 6. For I equals 5, the result is 5 equals 7. For I equals 6, we compute 6 equals 5, and finally, for I equals 7, the value is 7 equals 4. This gives us the gray code sequence 0, 1, 3, 2, 6, 7, 5, 4. Next, since the start value is 4, we determine its index in the gray code sequence, which is 7. To rearrange the sequence, we begin at index 7 and move forward, cycling back to include the earlier elements in order. This produces the rearranged sequence 4, 0, 1, 3, 2, 6, 7, 5. Therefore, the final output for this example is 4, 0, 1, 3, 2, 6, 7, 5. Finally, consider the third example where n equals 1 and start equals 0. Here, the total number of gray code values is 2 1 equals 2. Using the formula I1, we calculate the values. For I equals 0, we find 0 1 equals 0, and for I equals 1, the result is 1 1 equals 1. This gives the sequence 0, 1. Since the start value is 0, we locate its index, which is 0. Rearranging the sequence starting from this index, we obtain 0, 1. Thus, the final output for this example is 0, 1. The time complexity of this problem can be broken down into 3 main steps. First, the gray code sequence is generated for n bits. This involves iterating through all integers from 0 to 2 n1, which means there are 2 n iterations. For each iteration, the gray code value is calculated using the formula I1. Since this calculation is a constant time operation, the overall complexity for generating the gray code sequence is 2 to the power of n. Next, the algorithm needs to find the index of the start value in the gray code sequence. This is done using the index function, which may require scanning the entire sequence in the worst case. Since the sequence contains 2 n elements, this step also has a time complexity of 2 to the power of n. The final step involves rearranging the sequence to start from the given start value. This is achieved by slicing the sequence into 2 parts and concatenating them. The slicing operation for the first part takes k time, where k is the index of the start value, and slicing the second part takes 2 to the power of n k time. Concatenating these slices has a total complexity of 2 to the power of n. When combining the time complexities of all 3 steps, generating the gray code sequence, finding the start index, and rearranging the sequence, the overall time complexity of the code becomes 2 to the power of n, plus 2 to the power of n, plus 2 to the power of n, which simplifies to 2 to the power of n. On the space complexity side, the gray code sequence itself requires 2 to the power of n space to store, as it contains 2 n integers. Additionally, the intermediate variables like I and start_index take constant space, or 1. The output list, which contains the rearranged gray code sequence, also requires 2 to the power of n space. When we combine all these factors, the total space complexity of the code is 2 to the power of n for the gray code sequence, 1 for intermediate variables, and 2 to the power of n for the output list, resulting in an overall space complexity of 2 to the power of n. To put this in perspective, consider a naive brute force approach. Such an approach might generate all possible permutations of the 2 n elements and then check each permutation for the circular permutation property. This would lead to a factorial time complexity of O2 to the power of n, which becomes infeasible as n increases. In contrast, the current implementation is highly optimized. By leveraging the properties of gray code, it generates the required sequence in O2 to the power of n, time and space, which is significantly more efficient and practical. Let's now analyze the best, average, and worst-case scenarios for this algorithm. Regardless of the input, the algorithm always generates and processes the entire gray code sequence of size 2n. As a result, the time and space complexities remain O2 to the power of n in the best, average, and worst cases. This consistency is due to the predictable structure of the algorithm, where the dominant factor is the size of the gray code sequence. To solidify this understanding, we can look at the mathematical proof of the algorithm's big O complexity. For n bits, the sequence length is always 2n. All operations, including generation, indexing, and rearrangement, are bounded by linear scans or processing of this sequence. Since no part of the code introduces a higher order term, the overall complexity for both time and space definitively remains O2 to the power of n. When solving problems like this, it's easy to overlook some common pitfalls. For instance, handling edge cases such as n equals 0 or n equals 1 is crucial. These small inputs often test whether your solution fully respects the problem's constraints. Another frequent issue comes from misunderstanding the problem itself. For example, gray code requires that consecutive values differ by exactly 1 bit. Misinterpreting this can lead to solutions that seem logical but fail to meet the requirements. Additionally, inefficient solutions, like using brute force to generate all permutations, become infeasible for large inputs due to their exponential time complexity. Lastly, errors in bitwise operations, such as incorrect use of XOR or shifts, can easily lead to incorrect results. Bitwise calculations may seem simple, but they demand precision and careful implementation. Another mistake developers sometimes make is ignoring the constraints outlined in the problem. For example, if the sequence is required to start with 0, failing to enforce this can result in invalid outputs and failed test cases. Now, let's focus on how to approach this problem efficiently, especially in an interview setting. Recognizing that gray code generation can leverage mathematical properties, such as the formula G, I, equals I caret, I1, is a key insight. This approach reduces complexity and shows a strong grasp of bitwise operations. However, there are trade-offs to consider. Recursive solutions, while intuitive, can have higher memory and function call overhead, whereas iterative approaches using mathematical formulas are faster but require a deeper understanding of bitwise manipulation. Patterns like symmetry or self-similarity in binary sequences often appear in gray code-related problems, so recognizing these can help streamline your approach. For optimization, pre-computing gray codes for smaller values of n can save time if the problem involves repeated queries. Understanding related problems can further deepen your grasp of this topic. For example, LeetCode 89 is directly connected, as it focuses on implementing gray code generation. LeetCode 784, which involves generating all permutations under specific constraints, shares a similar combinatorial theme. LeetCode 46, dealing with generating all permutations, and LeetCode 78, focused on subsets and combinations, are also related. These problems often involve binary representations or recursive techniques, making them excellent practice for tackling gray code and related challenges. By exploring these problems, you'll not only strengthen your problem-solving skills but also recognize recurring patterns in permutation and combination problems. Finally, let's compare some alternative approaches and their trade-offs. A brute force solution, which generates all permutations, is straightforward to implement and guarantees correctness for small values of n. However, its exponential complexity, O2 to the power of n, makes it impractical for larger inputs. A recursive approach to gray code construction is another option. It's intuitive, as it builds the sequence by reflecting the previous one, but comes with higher memory usage and function call overhead. The most efficient method involves using a mathematical formula, such as G, I, equals I caret, I1. This approach generates gray code in O2 to the power of n, time with O1, space, making it ideal for larger inputs. However, it does require a solid understanding of bitwise operations, which can be challenging for beginners and harder to debug. Choosing the right approach depends on the constraints of the problem and your familiarity with these techniques. Great work following along. We explored the problem, discussed various approaches, and analyzed the pros and cons. Remember, understanding binary manipulation is crucial for many advanced problems. Thank you for joining, and don't forget to like and subscribe for more coding content. Until next time, happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!